Anissa,
Hello.
with the speakers in place, would you like to start?
Hello again.
Hello, good morning. So I think we have few people waiting in the waiting room, but they keep coming. So I would like to welcome everyone at the February Cape event, where we will have 6 presentations from Kappa Winners 2020. 2 presentations will be completed and 4 will be progress reports for the project that had to be delayed due to pandemic. And these 4 presenters will present again in June to give a final full report on their research. So first presentation will be PhD student Hanken Wang, who will present his project 3D deep learning for large-scale point cloud process. So Hanken, are you here?
Yeah, I'm just share my screen. Can you see it?
So thank you for coming, and you are welcome to start your presentation.
Okay. So yeah. So my proposed topics for the CAP award in last year is about. It's called 3D deep learning for a large scale point cloud process, and so basically a very short introduction is what is a point cloud. So essentially, a point cloud is a set of points that has been separated or located in the space. And it can be collected through devices such as LiDAR, which is widely used, which is a widely used data collector in the autonomous driving, and the depth camera, which is well, it's kind of largely used in the gaming um, industry to record the motions of humans. And it can be also converted from the other formats of the objects in the computer graphics, such as mesh or voxels, as well as depth map, 2D depth map. So you can see that our point cloud has variable, lots of resources in the collection, as well as a lot of as well as can be converted from lots of other object types representations. And so towards building up large scale point cloud, towards building up a large scale point cloud deep learning model, we're kind of want to solve this question by sorry, by
Anthony, would you like
propose
to put it on the full screen because your screen size is a bit small?
okay share full screen. How about this?
Yeah, that's better.
Okay, so want to tackle this problem by propose some strategies for unsupervised pre-training for deep learning models on point cloud. So unsupervised pre-training is widely used in deep learning these years for dealing with data such as language, uh, graph, and of course, and we want to use it for point cloud. And for the language, you might heard of BERT or recent or GP3, especially famous in last year. So for GP3, there's a large web engine, and you can type a few sentences, and it can help you like complete the entire paragraph of your sentences, or uh, potentially have a dialogue with you. Um, um, that is automatically generated by the trained GPT-3 model. And this is so unsupervised. It stands for that we don't need to provide labels for the training data. And the pre-training is like we propose generalized accelerate tasks that can be used to pre-train the model, and the pre-trained model can be shown that to be better faster to converge and to be and to have improvement on several downstream tasks, such as classifying an object, such as segmenting a thing, a parts of the thing into a class, such as you segmenting indoor point cloud scans into classes such as ceilings, tables, chairs, etc. And so to be more specific, our method can be has a diagram like this. So for our original 3D point cloud, we first to randomly select some camera viewpoints, and we use these camera viewpoints along with an algorithm called Z-buffering to generate a few occluded point cloud. And after that, you train a completion model, a deep completion model that takes the occluded object as input and outputs and complete the shape of the point cloud. And this completion model can be later used for different downstream tasks, such as classification and segmentation. And so now let's show some results of this pre-training. So the pre-training is about to complete uncompleted shapes and of the 3D point cloud. So the very left column is the input of our completion model. So it's a part of the object. So as the example shown as the left half, it's a cup, and our model output the complete shape in 2 steps. It first complete it's in a coarse and ends into a fine style, and the second column is the coarse output of the completion model, and the third is the fine output of the completion model, and this last column is what called ground truth, which is the shape that we use to generate this self-occluded objects. And for the right half, it's another example. So I think this is the example of the sofa, I think, yeah, or coach, and the input is a part occluded sofa, and our completion model can successfully learn to complete the entire shapes, giving a part observations of the point cloud object. And there's some more examples. So now the left one is a bottle, and the input is a half or a bottle. You can also think it as a bottle that you observed from a very specific viewpoint. And the right example is kind of bottle or vase. So it's you can see that our model can learn to complete the shapes for various object classes. But also we have some failure examples for the completion pre-training. So you can see that for the left example, it's a chair, but it has a bit artistic style for its leg. So you can see that our model can successfully recognize this object as a chair, since the completion results is still we can visually see that it's a chair, but it failed to capture the fine details of the object. For instance, it's recognized it's a chair, but it did not successfully show that it has this kind of shape. And the right example is similar. So we can see that the model can successfully recognize the table, but it fails to complete its legs, its support parts. So it's a very common which is 4-leg structure instead of the provided ground truth shapes. But yeah, so we show that even the failure example, our model can still capture that which class this object belong to, but might not be always successful to complete the fine structures of that object. And we show some empirical results on the downstream tasks. So a very basic task is called classification. So classification task is about given a 3D point cloud, the model need to predict the object class for that set of points. And we want the model to be as precise as possible. So we want the accuracy on the test set to be as high, as close to 100 as possible. And so the right upper hand is an overview of the dataset we use. One of the dataset we use to benchmark this baselines and with other pre-training method. And it's basically called ModelNet 40, which contains 40 different object classes and in a total of 8,000 objects. It's the first rows in the table. And our pre-training method is called OCO. So it stands for occlusion completion. And the RAND stands for random initialized. So it stands for your random initialize the weights of the entire deep networks, and you train them from scratch. And the Jigsaw is previously very famous pre-training method with OneStop. And we show that under these three different object classification dataset, and under three different baseline models that such namely PointNet, PCN, and DGCN. We show that our pre-training method has a better test accuracy, better test performance in comparison to previous method and random initialization on this classification task. And we're also doing more specific settings for classification task, which is called few shot. So few shot means your training sample, the number of your training sample is extremely small. So for a 5-way 10-shot, which means for each class of the 5 provided class, you only have 10 objects for the training, and you need to test the model on the entire test set. So you can think of it it's a quite challenging setting still in the classification tasks. And we show that in the few shot setting, our pre-training model, which is the last row called DGCN OCO, and the row called PointNet OCO, has better test or comparable test performance in collaboration with a few others pre-training method, and it's outperforms all the baseline models that with random initialization. And next, a downstream task is about called semantic segmentation. So basically, given a scan of the indoor scenes of 3D point cloud, the task is trying to predict which semantic class, which object class that points belong to. So, for instance, for this diagram, it's a scan of a kind of a meeting room, and you can see that the deep blue colors stands for kind of the floor of the meeting room, and the red stands for the chairs. The purple kind of stands for tables, and the green stands for the whiteboard. So this is basically a diagram, visualization of what this data looks like, and what we color them by their labels, by which class it belongs to. But in training the model, we only have the coordinates of the points, and we show that for this specific task, which have over like 24 rooms in total. Our model, our pre-trained method can still outperform the previous method in the different for all the different baseline models. And we also apply this on a very large scale outdoor point cloud data, which is yes, a part of them is collected from Cambridge by a team in Oxford, and so we still the same is very similar to the indoor semantic segmentation, but instead the object class might have different sets. So the object class is now become ground vegetation and building and etc. And our model still can outperform the random initialized baseline models in terms of the overall test accuracy and the mean intersection of unions over all the classes. And the last result I want to show that is the learning curves. So towards to do a large scale point cloud processing, a very common benchmark is called is to show that your model can converge faster or converge better in terms of provide an efficient and effective solutions for processing large scale point cloud. So in this 6 small figures, we basically show that our proposed pre-trained method called OCO can for different baseline models and under various tasks, it can converge a bit faster, as well as higher in the test accuracy in comparison with other random initialization method and the pre-trained method. So this is basically the main results of our work on proposing a pre-trained model for processing large-scale point cloud. Thanks for listening.
Thank you very much. Heinken, and I would like to open the floor to any questions. Anyone would like to ask something?
This has been done for a sort of bunch of applications in different groups around the world. Where do you see this being used for in your research? In the next 5 years, how will you use this in your research?
So essentially, we proposed a method, and this pre-trained method is potentially can be used for the model that is also going to be proposed in the next 5 years. So we proposed a method that can be used for pre-trained point cloud models, not necessarily to be the existing ones, but also for the potentially emerging ones. So if people are saying this pre-trained model is useful, they can use it as a better initializer for their proposed models instead of to initialize from random distributions. And I think this will be useful for the upcoming point cloud models in the future.
Okay, thank you.
Thanks.
Any more questions? Yes. If not, then we would like to thank the speaker. Thank you very much, Heinken. And we would like to invite the next speaker of the next project, which is Phoebe Shingao and Alkausil Tanboli. And their winning project is titled Simulation and Modeling of Piezoelectric Nanoscale Resonators for Sensing Applications, Nanobulk Acoustic Wave Resonators. So Phoebe?
Yeah, so I will share my screen with you. Okay, so hello everyone. So Kaush and me are going to present to you with our CAPA research project results on simulation and modeling of piezoelectric nanoscale resonators for sensing applications on nano-bulk acoustic wave resonators. So the fundamental mechanism that nano-bulk acoustic wave resonators employ is that the sound waves interact with matter, enabling sensing. It uses the propagation of waves in a medium such as the standing wave in a resonator. The use of sound waves for imaging is well established. One successful and widely applied example is the medical ultrasound diagnosis technique. With the nano-bulk acoustic wave resonators, the applications of which are carried further. So acoustic sensors are capable to achieve many tasks and applications. So here we just give some examples. So it can be applied in rheology to build a rheometer to measure the way in which a liquid in response to applied force. It can also make a cost-effective pollution monitoring device, or it can be used to constantly monitoring the structural conditions in buildings, bridges, or any infrastructure to avoid risks of structural failure. It can also be used in the lab-on-chip technology to detect antibody bindings, and this part we're going to introduce a little bit further later. The wide range of successful applications of acoustic sensors made the motivation of this project, which is to develop the acoustic sensor further beyond the existing techniques. So the bulk acoustic wave resonator is a type of acoustic sensor, and its basic structure is shown in the picture. It composes of two electrode layers and the piezoelectric layer sandwiched in between. So during the operation, an alternating voltage is applied on the top electric layer and the bottom electrode layer is grounded. The stress is the highest at the middle layer of the structure and lower on the outer layers. The stress is distributed as indicated in the graph. So the ability of the bulk acoustic wave resonators to measure mass changes originated in the discovery of the relation between the resonance frequency and the mass. So the relationship is shown in the formula, and it was formulated in 1959 by Mr. Salisbury. So the equation shows the shift in frequency is a result of the change in mass, and it also shows the relationship is linear. So one important application of the bulk acoustic wave resonator is the bulk acoustic wave-based biosensor. It employs the Salisbury's equation that was just introduced. So the biologic sample that is being tested are attached to the piezoelectric bulk, which would have a natural resonance frequency. When the antibodies were binded and the mass were bound to the resonator surface, the overall mass increases, which causes the frequency drop, as shown in the figure on the right. So the bulk acoustic wave resonators are also based on the piezoelectric effect, which is the property processed by certain class of crystals to convert mechanical stress into electric displacement. The inverse also holds true, which means electric displacement can also be converted into mechanical stress, and this is called the inverse piezoelectric effect. So I would also like to briefly introduce the thin film bulk acoustic wave technology, which is also part of the existing technology. So the thin film technology offers the following major advantages. So it is compatible with a range of substrates. It also enables CMOS integration and gives wave confinement, and it is able to work with a wide range of materials. The next section of the presentation, I'm going to hand it over to Kaush.
Yeah, sure. Thanks, Phoebe. Thanks for the introduction, Phoebe. And so the next section discusses how the acoustic confinement structure of the existing designs are available. And yes, there are two existing designs of the acoustic resonators. In the top one, in the figure A, you could see that there is a top and a bottom electrode and a piezoelectric transducing unit, which is being sandwiched between them, and an air cavity. And the bottom one has the same resonating structure, but only differs that instead of air cavity, there is a Bragg's reflector, an acoustic Bragg reflector introduced. So these reflecting mechanisms are to prevent the acoustic losses into the substrate, because when you excite these resonating devices, most of the acoustic energy radiates into the substrate, which is nothing but the loss of the acoustic energy, which could not be useful in the sensing application. So these are the two acoustic resonating devices that are majorly classified as thin film bulk acoustic resonators in the major designs. Yeah, the features of these existing designs are these devices have an active area of several hundreds of microns, and the operating resonant frequency is between a few hundreds of megahertz to 2.5 gigahertz. And this means that these are, though they are very small compared to very macroscopic devices, but there is still a lot of room to miniaturize these designs. And by miniaturization, one more thing we intend to achieve is to achieve high resonant frequencies, because if we are able to achieve high resonant frequencies, that means we would potentially be able to develop sensors which are very, very sensitive compared to the existing sensing technologies, compared to the existing resonating sensor technologies. Cool. So as I discussed, that the major objective of these projects is to miniaturize these existing bulk acoustic wave resonators, and the thing that we wanted to propose was a nanoscale version of these thin film bulk acoustic resonators. To achieve this, we used lateral field excitation. Lateral field excitation, as you saw in the previous picture, there is a top electrode and bottom electrode, and a piezoelectric transducing unit, which is being sandwiched between them. But in this project, as you will see in the coming slides, we have used the lateral field excitation using a coplanar electrode arrangement, which would excite the transducing layer laterally and not longitudinally, which would enable us to go for thin films. By thin films, I mean films in the range of nanoscale. For simulation, we have used a film of thickness 200 nanometers, but in reality, I think we would be able to go far below this. So yes, by achieving, it was just to enable higher sensitivities, and also the active region that we have used for our device is few microns that I would discuss. To design this device, we have used COMSOL multiphysics, and I would discuss the boundary condition that we try to use to simulate the profile of these devices. Maybe can we go? Cool. The salient features of the device that we proposed, the active region that we used to design this resonator based sensor was 2 microns by 2 microns, which is opposed to several hundred microns in the existing sensor technologies. And the operating frequencies that we obtained was between 4 to 5 gigahertz. So essentially, if you remember the formula that the Sobray's process, we would be able to detect masses smaller than several femtograms. So, which is actually far better than the existing thin film acoustic resonators. Yeah, and the thing that I discussed already, that we have used lateral field excitation. It also helps to achieve higher sensitivities, but also to reduce the acoustic losses and gain high Q factors. Cool. So here is the proposed device structure that we used. So we have a coplanar electrodes arrangement, and then we have a piezoelectric layer beneath it. And then we have a silicon dioxide layer, which acts as a passivation layer to prevent the acoustic losses. And then we have an air cavity to prevent the acoustic energy from getting radiated into the substrate. So yes, as I discussed, that this board design is laterally excited using the coplanar electrodes, and the lateral excitation results in the miniaturization of this device, and which could enable us to get higher operating frequencies. Cool. So for the design of these sensors, we have used COMSOL multiphysics, and the piezoelectric module was employed. Yeah, the analysis was done in the frequency domain, and the material we used was zinc oxide. Zinc oxide was used because if we want to go in real-time fabrication of this device, then zinc oxide is a really easy material based on the stoichiometric ratios to form, and also it's quite biocompatible. So if we want to go for biosensor based on these nanoscale bulk acoustic resonators, we just thought it would be really ideal to use zinc oxide for simulation as well. Yes, so these were the boundary conditions that we used for these acoustic resonators. As we discussed, like amongst the coplanar electrodes, the left one was given the AC voltage of 1 volt, and the right one was grounded basically. And the edges, we used a perfectly matched layer, which was then followed by fixed constraint. So the edges were mechanically fixed, and the air cavity in this was given the free constraint using COMSOL multiphysics so as to enable the vibration of the device. Cool. So you could see the two-dimensional model that we developed using COMSOL again. And here we are showing the displacement profile. So once you activate the device, you can see the oscillations very clearly that we got. And you could see that the displacement that we got was in like several picometers, which is better than the existing device, because in the existing device, you get the displacement of several femtometers. So yeah, we get higher displacements. And also the one main thing you could see is most of the acoustic energy is constrained within the resonating structure, and you could not see much of losses. Since we have developed the model, there is a lot of work to be done to see what actually the Q factors are of these devices. But for now, we have just decided to go for the displacement profile and the impedance analysis that I think I'll discuss in the next slide. Yeah, so this is one of the good news in this project, that we have got resonant frequencies beyond 4 gigahertz. And you could see that there is a fundamental mode that has been contributed by the zinc oxide layer, that is a transducing layer. And also there is another mode which we suspected to be contributed by the zinc oxide layer along with the silicon dioxide layer, which we are not yet sure about the second mode, because it requires a lot of experimental work and also a lot of work to be done on that. But we could clearly see that the resonating frequency of this device, the fundamental mode contributed by zinc oxide, is around 4.1 gigahertz. That literally means we could detect masses, really very small masses, which would be equal to the mass of a single virus, basically, which would be in several femtograms. And if we are suspecting that the second mode, which we get at around 4.7 gigahertz, is by the zinc oxide layer with silicon dioxide layer, if it is a dual mode, then yes, it could be used for temperature measurement along with the mass measurement system. So yes, so the results that we were happy about was that we were able to get higher resonating frequencies than the existing design. And we were also able to get dual mode to some extent. So hopefully in future, if this device is successful, then we may go for the fabrication of this device and actually see how in real time this device behaves. Cool. Thank you for listening, and any questions?
Danisa, sorry, I think you are muted.
Thank you, Phoebe. I didn't realize that. So yes, please, anyone, if you'd like to ask any questions. I have a question actually myself. How would you go about fabricating these devices? What methods would you use?
I think we would go for deposition techniques such as ALD, because these films are really thin. So we would go for the deposition of the transducing layer zinc oxide using ALD. And for etching to form the air cavity, we would go something like deep reactive ion etching.
I see.
And for electrodes, we would go for lithography.
Thank you.
I have a question, if I may.
Yes.
Where the resonators have been used to detect, for example, biological molecules, what's the proposal for cleaning the sensors so they can be reset?
Okay, yeah, so there are, I mean, there are actually very few startup companies that are coming out of Cambridge which are trying to commercialize these kind of acoustic devices. So even they are in the initial phases to actually realize that what could be the potential methods to use for cleaning. But I think you could go for like solvent-based cleaning. So the surface of this acoustic devices could, I mean, if you use metal passivation for this thing, you could use like solvents to clean the surfaces, something like as simple as acetone.
Okay, thank you.
Any more questions? If no, we would like to thank the speakers. Thank you, Phoebe and Alcaucil. And we would move to the next presentation, which is by Peter Christopher, Jamie Lake, and Ralph Mountain. And the title of their project is Focal Depth Tracking for Improved Three-Dimensional Holographic Displays. This is a progress report, and the final presentation will be in June. So, Peter.
Yes, I'll just find the share screen button. I want this one. Okay, can you see that clearly?
I can't see just yet. Does anyone see the screen share? Yep, I think it's coming up. Yes, I can see the presentation, yes.
Right, cool. Well, in which case, I'll begin. So I'm afraid if you're expecting something exciting today, then you are not in luck, because there isn't much to share. And so, but I'll get to that in a sec. So project title is that focal depth tracking for improved three-dimensional holographic displays. And what that translates to in real terms is eye trackers plus holograms is cool. So who am I? Well, my name is Peter Christopher. I'm a research associate at University of Cambridge. I'm soon to be a research fellow at Emmanuel College, and I'm a co-founder of Exobotics. And my real interest is in all things. Why is this auto-scrolling? My apologies. And the best thing about COVID for me is that I don't need to leave my armchair to do a presentation. But I'm actually presenting on the behalf of a bunch of other people who are actually the real heroes here. Can I apologize? This thing is not working as expected. Okay, I'm very sorry. We're having technical difficulties. Okay. All right, my apologies. We'll start again. Hi, I'm Peter. If you can hear me, give me a wave. I'm a research associate at University of Cambridge, soon to be a research fellow at Emmanuel College. I'm also co-founder of a space startup. It's not very exciting. and I like holograms. So that's me. But I'm actually presenting on behalf of a bunch of other people. Yes, behind every mediocre presenter is a team of the actually competent people who do all the good work. So the first is Jamie Lake, who's a PhD student and is project manager. Second is
your presentation, actually.
Oh, sorry. This has been a comedy of errors.
Not to worry.
Okay, does that work now?
Yes, I can see the.
Okay, I blame Microsoft. There's Ralph Mouton, who's a colleague of mine, and is the optical wizard behind it. There's Hannah Joyce, who's a reader in low-dimensional electronics, and there's Tim Wilkinson, who's a professor of something to do with timey-wimey holographic stuff. No one's really sure what. Unfortunately, I can't tell you anything interesting in this presentation. The first is because of COVID. All our experiments require multiple human participants, which has not been allowed at any point during the COVID. So we have been able to do nothing other than the theoretical back end. And while that's interesting, I can't talk to you about that stuff because we're still in sort of discussions about patents. So I'll very briefly introduce you to some holography, and then I'm afraid I'll have to leave you there because that is all I can say. And before we begin, I owe a shout out to the Observatory for Human Machine Collaboration, which has just started up on Mainsite, because they paid for this beauty here. So this is a state-of-the-art eye tracking unit. It sits in front of your computer. It doesn't look like much, but the price tag says otherwise. And it tracks you around the room in extremely high detail. And then the CAPE award, which we're presenting for here today, is kindly paying for the optical components that go with this. So you've all seen variations on a traditional projector. Your projector shows something on its display or its micro display that looks not too dissimilar from what you eventually see on the screen. It'll be distorted somewhat, there'll be some different contrast and things, but fundamentally it's the same image. Whereas in a holographic projector, you show something that, for all intents and purposes, looks like random noise. And in fact, it's very similar to random noise in many ways. And then the optical setup does a Fourier transform on this to show you a reconstructed image. Now, this has a number of advantages and disadvantages. The big advantage is it allows us to do 3D. Your reconstructed image can be fully 3D, and it can, from your point of view as an observer, be in the room with you. So it's not, doesn't have to be like, I don't know, an Oculus Rift or something where you're showing two flat images to each eye. You could actually see this, you could walk around it, and you would move as you'd expect. And it also solves a number of the problems with sort of current 3D tech. If you want to know more, you're in the right place. So the long-term vision for this is to go from like a handheld projector like this. So this is a small projector. It's actually in front of you here. You're seeing through the glass. And I recommend watching that video if you get a chance. And to go from that to holodeck. So something immersive where you've got holograms on all sides of you. So this is my incredibly bad quality artistic render, but the idea is that the man there in grey sees the man there in blue, and there's an array of projectors behind him projecting that screen. They individual at every angle, and you can see why my career as an artist was cut short. Apologies. And the fundamental technology behind hologram is these pictures are thanks to Jamie Lake, so I don't want to claim credit for myself. Is that you are passing, let's say, a series of planar wave fronts and behind. So typically that would be a laser, and what we do. You're passing it through a diffraction field, which in this case is a spatial light modulator or equivalent. And then there's a Fourier transform that occurs between that diffraction field to the replay field is what you see. So the replay field might be, say, a projector screen or the surface of your glasses or your eyeball itself. So this is the example you're most likely to see it in at the moment. Is move on to this one. Yes, yeah, your eyes are looking outwards, And at different depth planes, you're seeing different images. And typically nowadays, that's for a headset because of limitations in holographic technology. So these pictures are thanks to Jamie. So this is a good demonstration here of you can, by scrolling through here, and if you change the focus on your eye, you can choose which one of these objects you want to be in focus. And the key thing there is that on stereoscopic headsets, like say an Oculus Rift, that choice is made for you by the camera operator or the software you're using. Whereas here in a holographic headset, that choice is made for you by you. You can choose whether to focus on at different depth planes. And what we're doing is we're adding eye tracking to this mix. Now, eye tracking has been done before for different elements, including virtual eye boxes and things. We've got a new element that it can be tied to. It has some new algorithms, which I think are interesting, but no one shares my opinion. And there's a bunch of patents in progress. We're in conversations with a couple of companies. We're pursuing licensing. And it's a classic, I'd tell you, but then I'd have to kill you thing. So unfortunately, what I'd like to say here is I have to give you this amazing XKCD cartoon. So it's a new project going forward. I could tell you, but I have to kill you. I mean, kill you even sooner. And that's it. So I'm afraid it's keep calm and ask questions. Thank you very much.
Thank you, Peter, for this very interesting presentation, especially graphics. So please, does anyone has any questions?
It's okay if you don't, because I realize I haven't said anything that most of you probably don't know far more about than I do. So
I have a simple question. Is
yes.
In terms of costs, do you have any estimates of how much it would cost to manufacture these things?
What, the eye tracker or the holographic projector?
The holographic projector.
Varies wildly. So none of the components in the holographic projector are any more expensive than the components in, say, a HoloLens made by Microsoft. They're just used differently. The difficulty is they're not as readily available off the shelf because there isn't alternative markets for them. So everything in a HoloLens, well, almost everything, you could also find in a mobile phone or cinema projector. So that means R&D costs are high, but eventual production costs wouldn't be any higher. One exception to that is that current holographic technology requires massively more computational power than equivalent classical projectors and gives you on a per pixel basis lower image quality. And that's traded off against the fact it gives you full 3D and a bunch of other good things, but it comes at disadvantage of basically it requires more pixels per bit of how good it looks and more computational power. But again, that's stuff that's you can get off the shelf. So development costs are reasonably high, as any kind of research is, but the eventual production costs probably aren't that much higher than the equivalent classical machine.
Okay, thank you.
Side note on the eye trackers are expensive. So the latest generation of headsets are including eye trackers, and they're not that expensive because none of the bits inside an eye tracker are expensive. I mean, I think the most expensive thing is an IR LED, but because they're very low volume products at the moment, are expensive. So that projector I showed you earlier costs best part of 20 grand, and that's not the most expensive one that company sells, and that company isn't the most expensive on the market. But for production, again, the unit cost is probably under £100, which is nothing in the cost of a HoloLens.
The display is based on LCOS?
Yes, our ones, but when for this project, I'm not especially interested in the underlying display. It could be a DMD or something. The technology is about integrating what we know about your eye with the algorithms for showing something. So I use LCOS because I've got a load and they're possibly the most versatile product on the market at the moment. But if the new TI phase devices became available, it could work on that as well. And you could also run it on a TI analog device, amplitude device if you wanted, though you'd get a lot more artifacts.
Okay, next question is, can I imagine like 8K LCOS display being partitioned into like 16 and then giving you on a single plane like 6 full HD holographic display.
Okay, so you've got an 8K HKHMD, and
Yeah.
you're splitting up into 6 regions and then using them all independently as separate displays. Yes,
Like yes, okay, yeah.
yes, you could do that. How you'd use it would be a more difficult question. So you could imagine a case where you used a complicated waveguide to combine them to increase the field of view. That's definitely possible. Well, I say it's possible. It's not going to be easy. And I'm not sure it would be the best way to do it. I'd wager quite a bit of money that there were better approaches to that problem. But yeah, you could. I mean, I think probably the more interesting question is, could you do both eyes from the same LCOS device? And the answer to that is very probably. But again, I'd be looking at time multiplexing instead of spatial multiplexing, which is, I think, fundamentally a lot of the problems with the approaches people take to field of view is that whereas classical projectors are very strictly limited on whether a problem is spatial or temporal, that's not true for holograms. The Fourier transform in there means that you can rephrase almost every problem you tackle as either a temporal problem, i.e. summing lots of bad low quality frames together, or a multiplexing spatial problem, i.e. one very good frame. So I'd be looking at that temporally, using maybe something like a ferroelectric probably for that case, because yeah, waveguides are still only average in quality.
Thank you. Does anyone have any more questions? If not, we would like to thank Peter as a speaker. Thank you very much, and best of luck with the rest of your research.
Thank you, and apologies for the technical difficulties.
No problem at all. So our next speaker is Mengyuan Tian and Yabing Yang, and their project is titled Wireless Power Transfer System using High Temperature Superconducting Capacitor. So are you here?
Yes. Can you hear me?
Yes, we can hear you. Please share your screen with us. Yeah, I can.
Can you see my screen? Shall I start? Okay.
Welcome and please present.
Okay, thank you. Hello, everyone. I'm Jiabing Yang, working on the application of high temperature superconductors, supervised by Dr. Tim Cruz. I appreciate the opportunity to be with you today. I'm here to talk to you about the project progress of our research on a wireless power transfer system using high temperature superconducting capacitors. My presentation will be in 4 parts. We are going to look at the introduction, methods and results, progress summary, and next plans, respectively. There will be time for questions at the end of my talk. The wireless power transfer system, simply referred to WPT system, has different types. Non-resonant coupled inductors, such as transformers, work on the principle of a primary coil generating a magnetic field and a secondary coil subtending as much as possible of that field. This can happen only in a short range and often requires a magnetic core. On the other hand, the wireless power system transfer here means to transfer energy in a resonant inductive coupling way. Resonance coupling forms a tuned ALC circuit. Significant power can be transmitted with the primary coil driven at a secondary side resonant frequency. Meanwhile, this type of wireless system's efficiency depends on the quality factor of the inserted resonant circuit to a large extent. Thus, high-temperature superconductors, also known as HTS-coated conductors, are promising candidates for this job due to the almost zero resistance. Most relevant studies aimed at applying an HTS coil in the WPT system because it can carry significant current density and create a strong magnetic field. But few studied the effect of an HTS capacitor. Therefore, we propose that HTS-coated conductors can also be fabricated to a high-quality capacitor with much lower surface resistance in HTS thin film and a larger dielectric constant in the substrate layer. Let's move on to the methods. Due to the limited access to a lab during the COVID-19, we started our research for modeling. Using the finite element method, we simulated the coils and capacitors based on the actual geometry and materials. Inductance, capacitance, and the equivalent series resistance, the so-called ESR, are calculated at high frequencies. Figures illustrate the appearance of models assembled from superconducting tapes and common materials in the software COMSOL multiphysics. Specifically, we took copper as a material of conventional coils. Meanwhile, copper is also used as electrode plates, and glass is used as a dielectric. The two form a control capacitor. For comparison, HTS-coated conductors were utilized to fabricate a coil and a capacitor with the same inductance and capacitance. The two tables show the calculated results of the related parameters. Obviously, the HTS coil and HTS capacitor have much smaller ESR than the conventional ones, meaning there is a much higher quality factor in the superconducting resonance. It is worth noting that I consulted our colleagues in our division who did this kind of measurement. They also agreed these figures are quite reasonable. Next, the WPT system's equivalent circuit can be simplified as shown in the top figure. Then we put the component data we just got into this system, developed in MATLAB Simulink. Figure 6 plots the voltage transfer waveforms of the system assembled by different resonators. The left half is the input voltage, and the voltage on the load is on the right half. We calculated the ratio of the amplitude of the two ports voltages. It is saying that while the HTS coil in the resonance has improved the efficiency from 45% to 55%, the HTS coil working with an HTS capacitor in the resonance can further increase this figure up to 70%. That is to say, all superconducting resonance performs the best at a resonant frequency. Furthermore, we curved the transfer function expressed as a scattering parameter, namely the S parameter for different combinations in the resonance. It is very sure that the resonant inductive coupling WPT system is most effective at the resonant frequency. Also, the all superconducting resonance exhibits the highest transfer efficiency in a wide range near the resonant frequency, which is likely to benefit the tuning process of a WPT system. To summarize, we have designed the prototype of the WPT system, including a resonant circuit composed of HTS capacitors and HTS coils. Material type, geometry size, and transmission frequency are all considered. Then we have modeled all the components using the finite element method. The inductance, capacitance, and ESR at different frequencies are examined. Finally, the system model has been developed to estimate the transfer performance. The voltage transfer efficiency of different resonant materials at frequencies is calculated, verifying the significance of HTS materials. As for the next plans, the quality performance of the HTS capacitor comes to be further quantified besides the enhancement of the all superconducting resonance consisting of an HTS capacitor and an HTS coil to the WPT system is to be experimentally confirmed. This Gantt chart is to illustrate our progress. We hope that the pandemic will be relieved as soon as possible so that we can access the lab more often to complete the remaining experimental work. Well, this brings me to the end of my presentation. Thank you for your attention. I would be happy to answer any questions you might have. That's it.
Thank you. Thank you very much, Yabin. So I open the floor to any questions.
Okay.
This is actually ongoing project, so Yabin will continue till next year, till next few months.
Okay, sure.
Yeah, one quick question, if I may.
Okay.
Thanks, Yabin. You mentioned high temperature, but what kind of temperature would there be for the power transfer?
In the nickel nitrogen,
300 Kelvin or sorry?
In 77 K in the liquid nitrogen bus.
Okay, 77, not 300.
Yeah, not 300. Yes.
Yeah, thanks. That's helpful.
Thank you.
Thank you. Any more questions? If not, then we would like to thank the speakers. Thank you, Yabin. There will be another presentation in June, the final one, so we would be able to ask more if you're interested. So we move on towards our next speaker. I would like to invite Liam Bird and Dylan Maxwell and their project called 3-electrode electrochemical cell with integrated pressure sensor.
Yeah, just share my screen.
Thank you, Dylan.
How's that look?
Yeah, we can see the screen.
Yep. Okay, great. Yeah, so here to talk about the progress that Liam and I have made on our project to try and design, fabricate and test a 3-electrode electrochemical cell with an integrated pressure sensor. So 3-electrode cells are an important component in lithium-ion battery research. And so to first start, I'll go through the sort of main components of the lithium-ion battery. So the schematic here on the left, we have an anode on a copper current collector. Can you see the mouse? Let me get the pointer. Yeah, that's better. Yeah, we have an anode on a copper current collector, and then a cathode here on the right on an aluminium current collector, and that's separated by this membrane or separator, which with an electrolyte that allows the lithium ions to shuttle between the two sides of the battery. And so when we develop a new battery material, we typically test the material in 2 different configurations. So to begin with, we start with a half cell where we have the working electrode that we then test against a lithium metal electrode. So the lithium metal electrode acts as a both a counter and reference electrode, because we have an excess of lithium metal, meaning that when we electrochemically cycle this the half cell, the potential of the lithium metal doesn't change during the cycling, meaning that it can act as a reference electrode. So by measuring the potential difference across the two electrodes, the working electrode and the lithium metal, we can track the chemical changes and chemical reactions undergoing at the working electrode during the cycling. And then in a full cell, we then have, so this would be similar to how a battery looks like in your phone or laptop. We then have an anode and then a cathode, and we then use a potentiostat to measure the potential difference between the anode and cathode. But the problem there is then in a full cell, because the potential of the 2 materials are simultaneously changing, the potential difference gives us a measure of the it gives us a measure of the voltage between the 2 materials. But because both materials are changing, we can't track the chemical changes at each electrode separately. So what we can do is use a 3-electrode cell by introducing a third reference electrode, which in a lithium-ion battery would be a lithium metal electrode. And then by measuring the potential difference between the anode and the reference electrode and the cathode and the reference electrode separately, we can then measure the the voltage or track the voltage changes, the potential changes of both electrodes separately. And this is important because then we can track the chemical changes in something that simulates more closely a full working battery. And also in terms of studying new materials, the battery degradation mechanisms are not always the same when testing in half cell and full cell regimes. And so in our project, we would like to integrate a pressure sensor into this with two main aims. So the first would be to try and improve the reproducibility of the experiments, because so when you put together these 3 electrode cells, you typically have a plunger or some kind of pressure plunger essentially to apply pressure between the anode and cathode. And this is because stack pressure is quite important when assembling these cells. So because if the stack pressure between the anode and cathode is too low, then we can increase ohmic resistances, and if it's too high, then it may lower the battery performance. And the other thing we propose to do is to do some in situ monitoring. So I'll sort of go through this with an example of a material that has quite some interest in research at the moment, which is silicon. So silicon is expected to be the next anode material in next generation lithium-ion batteries, because it has 10 times, or can store 10 times more lithium than conventional anode materials, meaning we can increase the energy density of lithium-ion batteries using this material. However, it's not without its issues. So when you lithiate silicon in the first cycle, it can expand by up to around 300%. And at the same time, at low voltages, we get this degradation of the electrolyte that forms this SCI layer, or solid electrolyte interface layer, on the surface of the silicon. And then when we delithiate the material, the silicon then shrinks back to not quite its original size, but it shrinks. And then in subsequent cycles, when we relithiate the silicon, it then expands again. This SCI layer cracks and exposes fresh silicon surfaces, where more electrolyte then reacts and forms a new SCI layer. And over multiple cycles, we then get sort of this expansion and contraction that leads to, we get continuous SCI formation, and this leads to the eventual pulverization of the silicon particle, and then which leads to capacity fading and the eventual sort of failure of the battery. And so what we propose to do with the pressure sensing is by monitoring this in situ. So during the electrochemical cycling, we can then relate the measurement back to the volume expansion in the silicon, and measure and sort of get an idea of the stress evolution within the silicon electrode, and then correlate that back to electrochemical data to give a deeper understanding of battery failure mechanisms. Yeah, so I'll pass over to Liam now to continue the presentation.
Okay, thanks, Dylan. So as Dylan was saying, 3 electrode cells are really valuable tools in examining electrochemical behavior. So other 3 electrode cell designs have been developed in the past. Notably, there's a type of cell that's referred to as a swage lock cell. So this uses the plungers that Dylan mentioned earlier. You can see them to the left and right of this image on the top left. Yeah, thanks. Dylan mentioned reproducibility, and in terms of applying a reproducible amount of pressure when testing different cells. In this type of design, the 2 plungers are effectively tightened in opposition to each other, so it's quite difficult to control the amount of pressure that's applied to the cell. So the reference electrode in this design is introduced in the middle through a kind of probe-like wire, and it has a small piece of lithium attached to the end at a fixed distance from the rest of the cell, which is being tested. So the things that we'd like to change and improve on this design are trying to make it as easy as possible to assemble within the glove box, and specifically also trying to introduce the use of standard components that we have inside the glove box, and in particular, so using a piece of lithium as the reference electrode one of the things that we would like to try with our design is at the moment, at the end of the probe, like reference electrode, there's a small piece of lithium. If we could use a larger 14mm standard lithium chip, that would also provide a larger surface area, which would hopefully make the behavior closer to the ideal constant potential that Dylan mentioned earlier. So by changing the order of the components, it would also hopefully inherently make it easier to control the important difference, the key distance between the working electrode and the reference electrode. So in terms of making it easier to assemble inside the glove box, we've also changed the overall design of the cell as well. Can I have the next slide, please?
Yeah.
Thanks. So in the design that we're proposing, instead of adjusting the two plungers or the two electrode contacts in opposition to each other, we have a kind of vertical design. So we have two interchangeable electrode contacts to make it easier to manage the components inside the glove box. And we have the sensor down at the bottom of the cylinder. So the way that this is assembled is shown by this 3D view on the right. Yeah, if you could click once, please, thanks. So in assembling the cell, the first electrode contact would be inserted through the top, and then the cell stack components that you can see in the top left would be inserted on top of this contact, and then the next electrode contact applied on the top of that. So we have the seal that is provided by the two O-rings that you can see in green in the exploded diagram on the left. So to adjust the pressure that's applied after assembling the cell, sorry if you could just click it again. So the pressure sensor position would be at the bottom of the cell, and the contact by the electrode contact to the pressure sensor is through this hole at the bottom. So after assembling the cell, the cap that's at the very top of the exploded view can then be adjusted, and we can control and monitor the amount of pressure that's being applied to the electrode stack, so that the results are more reproducible, in addition to using the sensor to measure the changes in pressure as the cell is cycled. Yeah, can I have the next slide, please? Thanks. So obviously, like everybody else, our access to the labs has been quite limited. So far, the progress that we've made is we have the designs that you've seen on the previous slides, and they've been 3D printed in ABS to check that it's ergonomically easy to handle inside the glove box, and check that the components fit together. So the next step is to manufacture the effectively the final casing with proper seals for the electrode contacts and so on, and that will be manufactured from PEEK and stainless steel. After that, we then need to demonstrate that the electrochemical results that we get from this cell are comparable to those from either existing 3 electrode designs or from well-characterized electrode materials, to demonstrate that the cell is functioning as an electrochemical system. And then the next stage is to integrate the pressure sensor. So far, we've used a very cheap pressure sensor. It's effectively the same Wheatstone bridge electronic setup, and looked at ways to calibrate that type of pressure sensor. In terms of how we would use that inside the cell, it may be possible to look at kind of semi-quantitative changes in terms of like the starting and final pressure for a certain cell, or comparing the change in pressure for different cell designs. Yeah, so that's as far as we've got so far, and hopefully we'll be able to update you with some more results and outputs later in the year.
Thank you. So thank you very much, Liam and Dylan. I believe this is time for questions.
Yeah. Any questions? Welcome.
And, yeah, anyone would like to ask any questions, please? Actually, I have a question about the pressure sensor. Is it supposed to measure the pressure or to regulate the pressure in the system?
So it's supposed to measure the pressure, but in the initial stages of setting up, we can also use it to gauge how much pressure we're applying to the system. So
I have a question, if I may ask. What is the unique benefit of your pressure sensor compared to the state-of-the-art pressure sensors?
So at the moment, there are 3 electrode cells available, but they don't have pressure sensors integrated into them. Although you can, I guess, measure the pressure due to the expansion of the electrode materials, it's not, I don't know, Dylan, you can speak more about this.
Yeah, no, yeah. As far as I know, I've never seen a 3 electrode cell with a integrated pressure sensor.
Right.
So,
okay. So that's
yeah.
the thing. So it's integrated within the electric cell.
Yeah. Exactly. Yeah.
Okay.
And also, I could add some comment because in the 3 electrode sensors, we are possible to get a more reliable result because commercially the battery only have 2 electrodes. So actually, the voltage or some electrochemical information what you got maybe not that reliable. So if we add a reference electrode, it gives us more reliable results for the understanding.
Yeah, exactly.
Thank you. Any more questions, please? If not, we would like to thank the speakers. Thank you, Liam. Thank you, Dylan. And we are looking forward to your final presentation in June.
Thanks.
Thank you. Now I would like to invite our next speaker, Malar Chela-Sivaligan, who will be presenting her project Mastery of Microchip Technology to Tackle Air Pollution. Welcome, Malar, and please share your screen. I can actually already see it.
Okay. Hello all, I am Mala, a PhD student in the engineering department. Today, I'm going to introduce my project to you all, which is the mastery of microchip technology to tackle air pollution. I'm supervised by Professor Ashwin Seshia for this project, who's also my PhD supervisor. And I thank CAPE for funding this project and giving me this platform to introduce my project to you all. So let me start with a historical overview. Shown here is the Nelson's column in London in the year 1952. During the December month of the year, it was a period of cold weather, and when combined with anticyclone and windless conditions, it formed a thick layer of smog all over the London city. People were asked to stay indoors, as we are doing now. Even then, the smog penetrated the indoor areas and reduced visibility. Within 5 days, 4,000 deaths were reported. Most of the deaths were caused by respiratory tract infections, which in turn were due to lung infections created by the smog. The UK government investigated this further, and then the Parliament passed the Clean Air Act in 1956, because of which the Nelson's column in the London city looks like this now. So, what are the main contributors of this smog? One of the main contributors of this smog is the particulate matter, which was the result of burning coal by that time. Even now, these particles exist because of emissions from industries, vehicle exhaust like the diesel engines, aircraft engines, smoke, and so on. If you see this image, this is an image of a human hair under a microscope. This single strand of human hair is about 50 to 60 micron in diameter. And the particles or the particulate matter that I'm talking about are normally grouped as PM10 for particles less than 10 micrometer in diameter, PM2.5 for particles less than 2.5 micrometer in diameter, and ultrafine particles for particles less than 100 nanometer in diameter. In this project, I'm focused on the ultrafine particles, that is the particles which are less than 100 nanometer in diameter. And I'm using MEMS technology to detect the presence of these ultrafine particles. Currently, light-based commercial technologies are used for detecting the particles based on light scattering. When light falls on the particles, the light gets reflected back. Based on the reflected information, the size of the particle will be determined. But mostly the current optical technologies are limited because of diffraction limit, and they cannot go beyond 300 nanometer sized particles. Because if they tend to go beyond the 300 nanometer sized particles, the size of the measurement instrument and the complexity of the instrument itself increases. So over the past few years, research has been carried out to develop portable and chip scale sensors based on MEMS technology for detecting these particles. The MEMS sensor shown here combines the MEMS sensing element with the microfluidics, and shown here is a portable MEMS sensor comprising a silicon micro cantilever as the sensing element. And these are other MEMS sensors based on thermal transduction principle. And these have also been implemented in the form of an array, which is less than the size of a coin. And this one here is a portable MEMS prototype developed in our research group called as the MEMS impactor stage. A PCB board carrying the MEMS resonator attached to a chip carrier can be placed within this MEMS impactor stage. The particles can then be inertially impacted onto the MEMS resonators through the nozzle arrangement at the top. Previous work in our research group has focused on the square plate piezoelectric bulk acoustic MEMS resonator operating in its square extensional mode. The square extensional mode expands equally in all the four directions, with the red points being the sensitive points of the resonator. So if you note carefully, in all these MEMS sensors, the resonant frequency shifts based on the mass of the particles deposited on the resonators. This is very important because the current engine emissions or the air quality standards that have been set are mass-based. But we should note that this resonant frequency not only shifts based on the mass of particles deposited, but also due to fluctuations in ambient temperature and pressure. So in order to solve this problem, I propose using the coupled MEMS resonator as a solution. So what is the specialty of this coupled MEMS resonator? This simple mechanical beam coupler connecting the two MEMS resonators makes all the difference, which is nothing but this works based on vibration mode localization principle. In simple terms, we can model this coupled MEMS resonator system as a mass spring dashpot system. And if we assume symmetrical conditions, considering equal masses and equal spring constants, and the two masses being connected by a mechanical spring, the displacement of the two masses will be equal when a force is applied. In electrical terms, the amplitude of vibration sensed from these two resonators will be equal when a voltage is applied. So under symmetrical condition, vibration energy will be distributed equally between the two resonators. If we then try to create a disturbance or asymmetry in this coupled resonator system by introducing an additional mass, then the symmetry will be broken such that vibration energy, instead of being equally distributed between the two resonators, become confined to one of the resonators. This vibration energy confinement can be experimentally recorded by measuring the individual amplitude of vibration from the two resonators and observing the amplitude ratio. So for this coupled resonator system, these are the equations for the resonant frequency at the out of phase mode and the in phase mode. Similarly, these are the equations for the amplitude ratio obtained from this coupled resonator system when they are operating at its out of phase mode and in phase mode. Now let me explain about this coupled MEMS resonator design. So this is a free floating coupled MEMS resonator anchored at the four corners. And I have designed this MEMS resonator such that it operates in its Lamé mode as opposed to the square extensional mode in the previous work. I have chosen the Lamé mode because in this mode, the square plate extends in 2 directions and contracts in other 2 directions, because of which the volume at this mode will be conserved when the MEMS resonator operates at this mode, and higher quality factors can be obtained when the square plate resonators operate in this mode. Now, to test the sensitivity of the coupled MEMS resonators to the ultrafine particles, an experimental setup was constructed. So this is the experimental setup which I constructed with the help of my peers in the engineering department. And I would like to take this opportunity to thank my peers for helping me to construct this experimental setup and for helping me to carry out this experiment. So shown here is the soot particle generator comprising a burner arrangement. So this is how the particles will be generated. And the size of the soot particles that are generated can be adjusted by adjusting the flow rate of propane. The particles that are generated will then be passed through an aging chamber, and then they will be connected to the reference instrument, such as the differential mobility analyzer and the condensation particle counter. The soot particle output will also be fed to another differential mobility analyzer for fine tuning the size of the particles, that is 200 nanometer, which will then be fed to the MEMS impactor stage by inertial impaction on the MEMS resonators. The variations in amplitudes of the 2 individual resonators in the coupled resonator system will then be monitored using a 2-channel lock-in amplifier. Since there are 2 resonators connected together, we are monitoring the amplitude output from the 2 resonators using a 2-channel lock-in amplifier. Now this experiment here is a forerunner for the work which I have proposed for this CAPE project. So I should mention that these results obtained from this experiment also got published in the special issue of the journal Sensors and got selected as a cover story out of 328 articles published in that issue of the journal. So these are the soot particles that are deposited onto the sensitive points of the resonator when they are operating at their Lamé mode. For the Lamé mode, the red points over here are the sensitive points. So the aim of this experiment was to generate 100 nanometer size soot particles and test the sensitivity of the MEMS resonators to the generated particles. If we look at these soot particles in a microscope, these particles just appear as if they are a black dot. But while observing through SEM imaging, we can clearly see the size of the particles and the distribution of the particles on the resonator surface. So this is the size distribution of the 100 nanometer sized particles measured using the differential mobility analyzer, which is the reference instrument. And this graph shows the frequency and amplitude shift of the coupled resonators in response to the soot particles deposited for about 40 minutes on the resonators. So when I was doing this experiment, the frequency peaks didn't appear to shift with increase in particle deposition. So I wasn't sure if the resonator was sensitive at all to the particles deposited. But when the response was zoomed in, so it clearly showed the small shift in frequency and amplitude depending on the mass of the particles deposited. So this red dot over here, the red dotted graph over here shows the response from the resonator 1, and the blue dotted graph over here shows the response from the resonator 2. So considering the amplitude of the resonator 1 and amplitude of the resonator 2, amplitude ratio will be considered as the output metric to determine the mass of the particles that are deposited on the resonators. Then I compared the frequency shift based on the mass of the particles deposited and the amplitude ratio shift based on the mass of particles deposited. So here you can see the amplitude ratio shift increases and the resonant frequency shift decreases. If we compare the sensitivity factors based on frequency shift and amplitude ratio shift, it became very clear that the amplitude ratio output metric provided 3 orders of magnitude improvement when compared to the traditional frequency shift output metric. So the sensitivity of this coupled resonator based on amplitude ratio output metric has been verified for the ultrafine soot particles. Then the Allen deviation graph was plotted to compare the stability of the amplitude ratio and frequency output metrics by monitoring the shift in frequency and amplitude ratio for a 12-hour period. This is to monitor the variations in the amplitude ratio and frequency for long-term measurements. The point of using this Allen deviation plot is also to see what would be the minimum variations in the amplitude ratio and the frequency shift that can be obtained over time. So the minimum of these peaks over here shows that a minimum deviation in the amplitude ratio can be obtained as 0.00577. This then represents the amplitude ratio stability for long-term measurements in the coupled MEMS resonator system. Similarly, the best case frequency stability was obtained as 0.0297 Hertz. And then by combining the previous sensitivity data and this stability data, the input referred stability was calculated. This input referred stability is calculated to obtain the minimum mass that can be sensed based on the frequency shift output metric, which is the traditional method, and the amplitude ratio shift output metric. So while observing the minimum mass that can be estimated based on the frequency shift output metric and the amplitude shift output metric, it was seen that the minimum mass that can be estimated based on frequency shift is 2.16 picogram and amplitude ratio is 367.8 picogram. If you look at this graph, it is also clear that the amplitude ratio stays stable for long-term measurements, whereas the resonant frequency fluctuates, proving that the amplitude ratio output metric is a better one for long-term measurements of these ultrafine particles. And here this graph shows the mass estimated based on the coupled MEMS resonator equations that were calculated, which is then compared with the mass indirectly estimated based on the condensation particle counter, which is used as a reference instrument. There are deviations based on the mass, which is calculated for frequency shift and amplitude ratio shift. And these deviations could be because of the spatial sensitivity issues associated with the MEMS resonator, and can also be because of the non-uniform deposition of the soot particles on the resonator surface. But the input referred stability, which is the minimum mass, which can be estimated based on the frequency shift output metric and the resonant and the amplitude ratio shift output metric, is verified for this experiment. Now, the other important thing to notice in these resonators, when particles get deposited on the resonator surface, the resonator surface fills quickly. So if the concentration of the particles is very high, the sensor lifetime will be reduced. That is, we will have to replace these resonators immediately. So one thing what we did is, in order to test the lifetime of these sensors, we tried initially impacting 100 nanometer polystyrene latex particles at higher concentration onto these coupled MEMS resonators for 5 minutes on the first resonator and for the next 5 minutes on the second resonator to see what would happen in the coupled MEMS resonator system. For observing this response, we chose the in-phase mode of operation because the amplitude ratio starts at 1 for the in-phase mode. So what we have observed is, when particles were deposited on the first resonator for about 5 minutes, the amplitude ratio, which was initially at 1, tends to diverge based on the mass which is deposited on the resonator. Then when we proceed to deposit mass on the second resonator, the diverged amplitude ratio converges and tends to become 1. So the amplitude ratio starts at 1 and goes back to 1. So this proves the mass balancing capability of the coupled resonator system, by which we can extend the sensor lifetime without having to go for any other wet or dry cleaning techniques by extracting the resonator out of the MEMS impactor stage. So another experiment which we did is testing the sensitivity of these resonators to temperature. So if we look at this graph, when particles were deposited on the first resonator, the amplitude ratio varied, which shows the amplitude ratio output metric is sensitive to the mass deposited on the first resonator. Similarly, when mass was deposited on the second resonator, the amplitude ratio varied again. It also proves that the amplitude ratio shift output metric is sensitive to the mass deposited on the second resonator. But when we changed the temperature or varied the temperature, this amplitude ratio shift output metric stayed constant, which proved that this coupled MEMS resonator system is insensitive to temperature, but highly sensitive to the mass that is deposited on the coupled MEMS resonator system. So this proves the validity of using this coupled MEMS resonator system as a field deployment equipment for long-term measurements of ultrafine particles. So far, we have seen the ability of this coupled MEMS resonator system to exhibit 3 orders of magnitude improvement in sensitivity based on amplitude ratio shift output metric. And we have also seen what is the minimum mass that can be estimated based on the stability measurements obtained from this coupled resonator system. We have also seen the common mode rejection capability, that is insensitivity to the temperature and mass balancing capability of this coupled MEMS resonator system. So what exactly is the mastery of the MEMS technology in tackling air pollution? To know that, you'll have to wait until the next part of this presentation, which will be in the June event. So thank you for listening.
Thank you, Malar, for this very interesting presentation, and I would like to open the floor to any questions.
I have a question here. It's very interesting. Thank you. One thing wasn't quite clear. How do you do the selectivity of the PM with your sensor? Because you measure the mass, but can you actually distinguish the size of the particle?
Yeah, so in these experiments, we didn't test the selectivity, but then we were focused on the size of the particles, which is the ultrafine and the particle size less than 300 nanometer. But the selectivity of this MEMS resonator to the particles can also be tested if we tend to look at the initial frequency response, which can be obtained from this coupled MEMS resonator system to different particles. So that has not been shown anywhere, but that would show you the difference for different particles. So based on that, one could say which type of particles are there on the coupled MEMS resonator system.
Okay, thank you.
Yeah, I have shown the long-term measurements based on the particle deposition. But as you asked to see the selectivity, we will need to look at carefully the initial measurements obtained from the coupled MEMS resonator system to consider how it is selective to different types of particles.
Thank you. Any more questions, please? If not, I would like to thank Malar. Thank you very much. And we look forward to part 2 in June, to your final presentation.
Sure.
Thank you. So this was our last talk, and I found all presentations are very interesting. So I would like to also mention that we have issued yesterday a new call for CAPA 2021, and the deadline for the applications is on 19th of March. So we look forward to receive more applications and see more interesting projects.
Thank you very much. I just want to say the thanks to everybody for the excellent work and also very interesting presentation. And I think we will put your presentation onto the website of the CAPE, and Denisa also start a YouTube channel, so probably we can put it there as well.
Yes, we will do so.
Okay.
So thank you very much, everyone, and yeah, we look forward to seeing you in the next CAPE event in June. We will circulate again the invitations. Thank you. Bye-bye, everyone.
Thank you very much. Thank you all.
Bye. Thank you. Bye.
Thanks.
Bye.
Bye.
Thank you. Bye.